In this recording, we will be talking about the decomposition of the time series. So the decomposition of the time series, it's a pre-processing step that prepare the data for modeling. And after we did the adjustments, transformations, and differencing, the next step is going to be the decomposition. And as we said, it's a pre-processing step. It helps visualizing trend, seasonality, and noise. Also, it guides the model choice. And it tells us about something about the residuals, which is the noise. And the decomposition separates the data or the time series into three components: the trend cycle, the seasonal, and the remainder, which is the random component or the irregular component. And we will be talking about two main methods. It's the old classical decomposition method, and the other one is the more advanced flexible method, which is the seasonal trend using one of the regression techniques. So the classical decomposition is simple and historical, and it assumes that the seasonal pattern does not change from year to year. It just repeats exactly every year. And there are two main forms of this classical decompositions: the additive form and the multiplicative form. So the first one, it's decomposing the time seasonal remainder as in way, the other one in a multiplicative way. The additive decomposition, the steps of doing that: first we have to compute the trend cycle t hat with using moving average. The width is 1 month or 2 months window. Then we do detrending by subtracting the two values, yt, the actual value, minus the t hat value. Then we find the seasonal component s hat by averaging the detrending values for each season. Finally, we compute the remainder using this formula by just subtracting the actual minus t hat's s hat. And if you look at the example, we can see that the employed or the retail employment, US retail employment, as shown in the first series. The first one is the one that contains the real series, just the time series. The other one is these are the three components separated in additive way. The trend is here, the seasonal is here, and the random here. Sometimes when we separate them, we still, for the classical, sometimes we see that, the random is still not random. There is some kind of a behavior there. So we did not completely separated them well. So in this case, we do something else. The second part, which is the multiplicative decomposition, the way that we do it is just we estimate the trend cycle t hat using the moving averages again. We do detrending by dividing now. Before we subtract, now we divide because it's multiplicative. Yt over t hat. Then we estimate the seasonal indices s hat. After that, we compute the remainder by just dividing the actual by the multiplication of t hat and s hat. There are issues with the classical decomposition, so we are kind of limitation. The first one is the classical decomposition relies completely on moving averages to estimate the trend. Because moving averages need observations on both sides, we lose many points at the start and at the end of the series. For instance, if you have monthly data and m equals 12, or the width equals 12, we cannot estimate the trend for the first 6 months and the last 6 months. They're kind of a blank, as we've seen before. This means that the model cannot tell whether what's happening in these edges. And as we know, some of the most important points are the most recent values, right? So if this doesn't tell you anything about the last 6 months or whatever, then we have issues. The second thing is moving averages smooth the data so heavily in a way that the sudden shifts, it's like they are flattened. Example about this is what happened in COVID-19 or 2008 crisis. In this case, the estimated trend does not react quickly enough. As a result, the decomposition underestimates how severe or sudden these changes were. The third limitation is that classical decomposition assumes that the seasonal pattern is identical every year, and this is not the case in reality. In reality, the patterns evolve. So, and very famous example about the electricity demand. Like 20, 30, 40 years ago, the peak was in winter. But now, because of the heating. But now the peak in summer because of the air conditioning. So there's a big difference between the seasonals, right? So the Classical decomposition cannot adapt. It keeps just using the same seasonal shape like every year. Also, the classical decomposition is not robust. For example, a single, let's say, unusual event like a pandemic month, let's say, can throw off the entire seasonal or trend estimate because it relies on averages. Again, because it relies on averages, so it should treat extreme values as part of the true pattern. And this is the issues with the average as a measure. It's sensitive to outliers. And classical decomposition uses averages. The last thing is the classical decomposition also was designed to use for simple single season data, like monthly, quarterly. It doesn't handle multiple seasonalities. Sometimes we have daily and weekly cycles. Or sometimes we have irregular data frequencies. And in modern business data, we have overlaps between seasons. And classical decomposition cannot capture this. That's why we switched to what's so-called STL decomposition. STL uses the regression to estimate the trend and seasonal parts, not the smoothing average. It's far more flexible compared to the classical decomposition. The seasonal pattern can slowly evolve, and we can control how smooth the trend should be. And this is in the same example we used using STL decomposition. You have the employed data, then we have the trend and seasonal and remainder. And if you look carefully on the trend and the remainder, they are different than the one that we have seen in the classical decomposition. So this is everything about the STL versus the classical decomposition. So by finishing this, we have completed all of the pre-processing techniques before we start doing modeling for the time series. Thank you.